All right, hey everyone, Math 6620. The purpose of this video is, I guess, fourfold. First thing, I want to introduce you to carrying out path analysis using R. We're going to go through some packages that we have to install. I'll explain a little bit about the data set. Something else I want to do is show you how closely what we're doing here is just an extension of multiple regression, and then we'll get into the output using the Lavon package in R and try to help you out in terms of understanding what the output tells us. Now, again, I think of this as we toss out a theory and we use structural equation modeling to test our theory. So I'm going to have a theory here that grit problem solving in algebra are somewhat predictive of trig, which is predictive of calculus. So you might think we have a couple of dependent variables here for the first part of the model. Trig actually serves as a dependent variable, and then for the overall model, calculus serves. So I think the model may have been better if I had had grit and problem solving as the only exogenous variables, and then algebra as the first endogenous leading into trig and then leading into calculus. But I think this is also a reasonable model to test as well. So we have some different components here, right? We have, again, if we look over here, we have for grit, we're going to have the variance components for each of our exogenous variables. We have our covariance components. We have our path into trig, and then our path from trig into calculus, and then we have our disturbance terms, the residual errors for each of our endogenous variables. So the data set I am dealing with using contains 5 variables, and you can see again the relationship we're testing to the left. Now, something I like, if we'll install this package core plot, and you know, I've got a lot of stuff I'm going to go over, but let me quite a bit, a lot more than I realized. But we'll try to get through that. So let's go all the way up to the top and look at, we've installed core plot, the library, and then we get a method for examining the correlations. Now, I really don't, because all of my variables in data set are quantitative, I don't mind running this command on the full data set. If I had some categorical variables in there, I may want to delete those using things that code that we've talked about earlier. So if I run this, I really like this design because you can see the bluer it gets means higher correlation. Of course, everything is going to be highly correlated with itself. So we can just eyeball this and see that calculus and algebra are and algebra and trig and calculus, algebra and trig. I'm sorry, algebra and calculus and algebra and trig are somewhat correlated. It looks like trig and grit and trig, well, are not correlated. So these are positive correlations. Negative correlations, of course, would be in the red. So I like running that just to get an indication of the relationships, because again, one of the assumptions is we have linearity. So the next thing I'm going to look at, well, the next thing I need to do is install the Lavon package. So you'll install it the first time, and then from there on out, you just have to access the library. So I'm going to create the first model. And again, I'm teaching here. This is not necessarily what I would do if I were running the analysis for my research, but this is what I'm going to do in terms of teaching. So if you see, let me get rid of this. You'll see what I'm doing here is I'm setting up a model, and we're going to manipulate this throughout the video. But right now, I just want to model trig as a function of grit, problem solving, and algebra. Now, again, we're not running a linear model or GLM commands as we've done previously. We're just establishing the relationship between trig, the first endogenous variable predicted from the other 3, grit, problem solving, and algebra. Next thing I'll do is I'll create my model fit, well, my model 1 fit. Structural equation modeling, the model that we created up here, and just make it clear what data set we're using. Next thing we do is we'll run a summary, and I want you to ignore this, okay? What I want you to do is when you run summary, I want you to specify these three. All right, so the fit measure, true, that just says that we have a saturated model with no degrees of freedom, which will change soon. The R square is nothing new. It's the adjusted R squared. No. I take that back. It's the unadjusted R squared, as we're typically used to seeing in simple linear regression, multiple regression, and the standardized give us standardized path coefficients. All right, so let's jump in to the summary of our model. First thing that we notice, or at least that I notice, we have 73 observations. That's our sample size. Next thing I see is that the model test has degrees of freedom 0. What's this? This is saying is it says we have a just identified model. In other words, the specified, I guess, a specified relation that we have identified in our model is kind of the best we can do, is one way. I can say it, surely I can say it better than that. I guess we're saying that the specified number of free parameters is equal to the unique pieces of information in our covariance matrix. What that tells me is, what does it tell me? When I have a degree of freedom 0, okay, we're supposed to just identified model. Okay, that tells me that these interpretations from here to here are meaningless to us. Now, later on, we're going to get degrees of freedom greater than 0, and then we'll dive into what all this information gives us. So fast forward down to the regression coefficients. Luckily, these things are interpreted just as we're used to interpreting in a linear model. We can see that grit has a negative relationship and not statistically significant with trig. Problem solving has a positive relationship and statistically significant at the 0.05 level. And algebra has a positive relationship and statistically significant at the 0.001 level. So the free parameters here are the grit, the problem solving, and algebra. Now the variance components is just the disturbance term that we talked about before. That's this residual error right there that we identify in path analysis. And it's statistically significant, which is really not of much interest to us at this point. The R squared, not a lot to say there, just as we would think, 51.4% of the variance in trig is explained by grit, problem solving, and algebra, of course, for this sample. Next thing I want to do is I want to add in the covariance terms. So I've pretty much specified the relationship between this part of the model, but you can see that we want the variance components and the covariance components. And the way I do that in R is I'm going to keep what I have previously in terms of modeling trig as a function of grit, problem solving, and algebra. But to get the covariances, I have to use a double tilde command. So note double tilde there, not just one, as we're used to doing in other code. So this gives me the covariance between grit and problem solving and algebra. So I also need it between problem solving and algebra. So that is the reason for adding that. I'll just keep it the coding the same, so model 1 fit as we did before, and then make a summary of our model just as we did before. Nothing's going to change, but you'll notice, well, better at least, our regression coefficients stay the same. I can't see why they would change, but you can see that we get some extra information, and the unadjusted R squared stays the same. So you can see where we get some additional information in terms of covariances and variances. So the estimated covariance between grit and problem solving is 26.53. Significant at the 0.001 level, and we can make similar statements for the rest. The variance component gives us extra. Above, I'm pretty sure we had the variance for trig only, right? Yeah. So now we get the variances for grit, problem solving, and algebra, our exogenous variables. So those are things that we will want to report in our path in the very final step. Now, the next thing I did here is I want to show you how this is actually very similar to things we've done before, done previously with simple linear regression. So I'm just going to use the LM command and model trig as a function of grit, problem solving, and algebra, and run the summary. And you can see that, notice that the coefficient for grit is negative 0.14, and up here, of course, the coefficient is negative 0.14. Standard errors will be the same, 0.12. Actually, yeah, the standard errors are the same. Now, one thing you notice, the test statistic is negative 1.186. Our test statistic down here is different. Notice that we're modeling with the t-distribution here versus the z-distribution up here. So the test statistics and the p-values are going to be slightly different. Like, for example, grit is 0.236. Grit in the simple linear regression or the multiple regression output is 0.253. So a little bit of difference, but the significance levels do not change in this example. But again, we're not doing linear models here. Simple multiple regression. We are studying a more complex design in for path analysis. Now, what I've done next is I want to now put a focus in on our model, right? So this is what I've hypothesized. The grit, problem-solving, algebra collectively explain variation in trig, and then trig, of course, explains variation in calculus. So I'm testing that. So you'll notice that the one relation that I had before, I'm keeping. You'll notice that the variance and covariance components that I kept before, I'm keeping. But you'll see here I've added calculus as a function of trig. Now, let's just say, for example, that instead of trig, I had algebra here. So let's say I had problem-solving grit leading into trig and to algebra. Well, I would just make the modification here. So it's very simple just to to model the paths that we are interested in examining. Same thing, model fit, structural equation model for the SEM code for model 1 data equal data, and we run our summary as before. Now, let's, what do I want to do now? I'll tell you what, let's do this. First of all, the number of parameters, and you'll see that previously this this model test user model. Let's scoot back up here. Model test user model had degrees of freedom 0, which gave us some important information. But now you'll notice when we're specifying the full model, let me find where I was, that we have degrees of freedom equal to 3. So that tells us that this information from here to here is actually useful in determining the effectiveness of our model. Now, the number of model parameters, 12, the way we come up with that is we have 12 estimates that we're making over here. The first estimate we make are variances. So we have 1, 2, 3 variances that we estimated. Then we have 1, 2, 3 covariances that we estimated. So we have 6 estimates right here. We have 7, 8, 9, 10. So we have 4 path coefficients we're estimating. And then we have 2 disturbance terms. So again, 1, 2, 3 for the variance, 4, 5, 6, including the covariance, 7, 8, 9, 10 for the path coefficients, 11, 12 for the disturbance terms or the residual errors. So that's where we get the number of model parameters. Now, the degrees of freedom, what we do there is we're actually looking at the number of estimates in the upper or lower triangle of the covariance matrix, and we can estimate the number of those by taking uh, uh, the number of parameters times the number of parameters plus 1 divided by 2. So we have 5 times 5 plus 1. I'm just going to put this, we all know it's 6, divided by 2 is going to be 15. So if we take the number of estimates here minus the number of model parameters that we have specified in our model, we get 3. Well, that is the degrees, or better be. Yeah, okay, that's the degrees of freedom that we have specified or calculated for a model. Now, what that tells us, again, is we can interpret these values. And there's some cutoffs that tell us whether we have a good model or not. Well, shouldn't say a good model, but I would say an effective model. I tell you what, this is going to take a while because there are some cutoffs I need to explain. I'm going to end this video and then take off where this video ends in the next video. All right, take care.